Go ahead and pull over your class docs repository. There's a couple new slides that I added to the slides that we were working on last, what was it now, Tuesday, I guess. And so I just made some updates, and so I wanted to go through those today. And also what we're doing today is we're going to be talking about, welcome everybody, by the way, welcome. We're going to be talking about one of the labs we worked on before, actually one of the vaccine lab. I wanted to spend some time actually just talking about that. So just to show you which slides we're working on these ones here from the 10th of November, which was last Tuesday, I believe, or at least the ones we were working on last Tuesday. And so if you pull those over, you should get an update that comes to this slide. So if you have this slide deck already open on your machine from somewhere else, please pull it over and then check out the new version of this slide deck. These are the slides. So anyway, you have those. Okay, so let's go ahead and get back to where we left off. And so what we were doing is actually we're working with these multiple variable regression. Let me get it bigger here so that everyone can see. I don't know if you can't see that. Maybe you can. Okay, so we're working with a multiple independent variables in a regression model. And really what that means is that we're looking at not just like, a y equals mx plus b type of line equation that we were working with before, but rather now we're looking at y equals mx1 plus, mx2 plus mx3, or sorry, m1 x1, m2 x2. It's like we're looking at different variables. And so here we're looking at this y is equal to b naught plus actually it's not b, it's beta. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. And we can do that for as many variables as we'd like to work with. Now each of these x1, x2, x3 that I'm looking at here, these are all the different variables that I'm throwing into my model. And so the reason why we're doing this is because we had these kinds of questions to work with. And one of the questions was, for instance, do age and IQ scores effectively predict the GPA? Now, in order to answer such a complicated question, and it is a very complicated question, in order to even to attempt to add it, or to find an answer to this question, we would have to look at not just one variable but several variables. And by that I'm talking about, for instance, you might have to look at many different factors that affect things like IQ. And if I'm looking at IQ here, you can't really measure IQ with just one variable. And so you have to use several different ones. The same thing is for the next question here, like for instance, the cholesterol levels. We're looking at how do weight, height, and age express some kind of variance in cholesterol levels. And again, we're looking at multiple things here, not just one. We're not just looking at how age affects cholesterol levels, if you can make such an assessment. But we're looking at like weight, height, age, and maybe even you can even add other things too in here, like maybe dietary conditions, or for instance, the amount of exercise that you get, or for instance, do you have a stressed life? Is a stressful life, or is it a stress-free life? And what kind of life do you live? And in order to answer those types of questions, again, you have many, many more variables that you could consider to respond to, for instance, how cholesterol could potentially affect, or how your cholesterol levels could be potentially affected here. So what I'm saying is there's not just one variable, but there are many. Another interesting thing is like this question here, the third one: are video game sales explained by their exciting graphics and inexpensive costs? Well, again, you could argue that it's not just perhaps the graphics that a game has and the cost of actually buying the game. It could be other things too. It could be, for instance, the playability if such a thing exists, or the interest in the game, or whether is the game the second game of a series of already an understood and well-known theme. So are there other things that contribute to whether a game sell, or a type of a game sells better than another game? So anyway, we have a whole bunch of variables that we can consider to answer each of these types of questions. And so for that reason, we have this kind of an equation here where you're throwing in multiple variables into your linear model equation. Now, this is different from last time, for instance, where we were just looking at one variable, and that's where y is equal to mx plus b equation came from. But now this is a little more complicated. And so this doesn't necessarily give you a straight line when you're working with your data. Rather, it gives you maybe a curvy line that moves around and does some interesting things. But it's still a line, nonetheless, that does become your model. And so the idea is that you can put in some values of x, and you can put in some, and you can see what happens to your y when that value of x is inserted into your equation. Anyway, I think you guys kind of get the idea about where that is. The line equation does look a little bit longer, but I can assure you that basically it's this piece right here, y is equal to that b naught, and then there's this next piece over here, which is the first term. And so in the past, we would just have this term, or these two terms here, followed by this term, and that would be our equation. But now, with this multiple variate equation, we have these extra terms thrown in. So what I'm trying to say, though, is that it's actually the same kind of, it's the same theory, if you will. It's the same theory, but we just have more variables to consider. Now, another thing that is also the same, which actually looks a little bit more complicated, but it's still, I can assure you, still the same, is that these beta variables here, in other words, these variables here, beta, these are the slopes that we have in our equation. And the slopes, in this case, we can't really call them slopes, we call them coefficients, but actually they are types of slopes which affect the variable that's next to it. But these are the coefficients, and so what we're doing is we have to create, a null hypothesis, which is going to somehow answer the question of whether age, height, and weight affect cholesterol levels, or how do they affect cholesterol levels. Where we have to create a hypothesis to say that yes, there is some kind of change that happens, or there is some kind of an interaction that happens between the independent variables and the dependent variables. And so here, the null or nothing hypothesis, null hypothesis, is that we're saying that all these variables are actually equal to 0. In other words, that when you have this equation here, when you have a bunch of zeros placed in, like for instance here and here and here and here, then if this whole thing is 0, then nothing is changing. In other words, the equation does not have any. There's no effect between the independent variables and the dependent variables. That's when these are zeros. And that's why we call this our null hypothesis. Now, the alternate hypothesis that we're talking about for this particular equation is that these variables, these beta variables, or these slopes, if you will, do count for something. They do contribute something to the equation. In other words, they are not 0. And so our model is really just giving us, the mathematics is just giving us, yes, these betas are 0. They have no effect. The independent variables have no effect on the dependent variables. That's our null hypothesis. But the alternative hypothesis is that they're not zeros, and they do have some kind of an effect. And so they are, something is happening, something's going on. And remember, though, that you can see whether or not you should accept the null hypothesis or the alternate hypothesis according to the p-value, which we get out of our summary from our model. Anyway, so we began working on this equation, or this lung capacity experiment, where we're looking to see whether age and height as variables in our data set can somehow affect our lung capacity. Now, it makes sense that they do, but we're trying to actually figure out that according to this data, how does the age and height actually make that effect? Like, what kind of effect is it from age and height? So maybe we just go ahead and try this out again. Maybe I'll just get us, I'll go back to our studio, and hopefully you can see if I transition to there. There you are. You see that? Yes, you are. Okay, so what I'm going to do is, we have this code right here. In fact, I think this is the exact same code that I've actually got in my slides, where we're just opening a file, and then we are defining that file as a CSV variable, I guess, which we open by the read CSV function, which then actually loads our data in. So this is the data. Where did I open it? It's right here. Okay. So I'm going to remove my old variables. Hopefully you can all see where I am. And then I load my tidyverse. You have to load your tidyverse. I'm going to open the psych library just because I may have to use it later on, but anyway, it doesn't hurt to open it now. I'm going to load my variable that's actually going to be in the file name and path that has the data. So you can't see what I'm doing, but I'm actually going to that lung cap file that you have in your sandbox. So you should have this. Now, I should say that one more thing is that if you see in the global environment, you just see LC. That's just my lung capacity file. It's just a file. It's not the data. It's just the name of the file. I actually load that data by this line here. And so that's, I'm saying this because I had an email yesterday that was somebody was working with they're working on these notes, and they had this right here, and then they moved into this line here, and they had forgotten to put this line in there, and that means that they were not able to actually open up the data. So you do have to use this read CSV function. Now, once that's done, you can see again in your global environment. I don't know if I can get this off the screen. Sorry, guys, on the screen, I'm getting all this stuff on here. I'll move this. I don't know what helps there. I can't. Maybe it's not left-handed. I can't move my hand around. I can see it here. Can I minimize it? There we go. Yeah, that's better. All right. Hopefully you can see a little bit better. Excuse me. So anyway, now that I have my data open, I've read the things as CSV. I can go ahead and actually view my file. This is the data that you should have on your screen if you follow that same code. So we have lung capacity. This is some measurement of the volume, of how much air can actually be held inside lungs. Interestingly enough, I'll just tell you that if you study marine biology, if you look at like the lungs that a dolphin has and the lungs that a person has, I think they're about the same size, but dolphins are actually able to fill their lungs with more air and get it out, whereas people, we don't have that capability. So props to our dolphin friends. They can actually take in more air and then push it out, and they can actually, their lungs are more efficient, even though they have similar types of capacities than what we have. They're actually able to get to all the air in their lungs. We have the variables age, height, smoking, gender, and cesarean. And so we can use these kinds of variables to aggregate our data and see whether, for instance, how do age and height affect the lung capacity, but also does smoking and does the gender and if someone was a cesarean, if they were born cesarean, does that make any difference either? I believe that's what it means if someone is born cesarean. Anyway, so we create our model actually on this line here. And so the model that we're looking at is actually, of course, you have to define the data. But then I'm actually looking at the lung capacity, which is going to be my dependent variable. If you think of this in terms of like this tilde as a kind of an equal sign, y is equal to mx plus b. These are the independent variables. So age and height are independent. And so when I run this, I get this model that shows up. No errors show up down here, which is exactly what I want. But if I look at the summary, then this is where things get interesting. So for instance, I can see, of course, from the call, this is what the model is. But I can see, for instance, that I'm looking at my p-value. This is significant. That's a very small number. It's between 0 and 0.01, which means I'm within the 99% confidence range. And so I know that this model is actually significant as it stands. But another thing, though, that's interesting is that we have age and height, which are already quite telling of how lung capacity is influenced. But another thing that we should really concentrate on, though, is this adjusted R squared. This is saying that about 84% of our model, or rather our dependent variable, is explained. In other words, the variation of our dependent variable by our independent variables, 84% of that can be explained by age and height. However, because we have an 84%, that would suggest that there is 15% of our model which is still unaccounted for. And so what that means is that there's still a piece of our model that we could add. Maybe it's age, maybe it's height, maybe it's the diet that somebody has, maybe it's the amount of exercise they get. I mean, it could be anything. And so what we would have to do is we'd have to start throwing in or finding more data to throw into our model and see whether or not our adjusted R squared value climbs any higher. But one thing I should say, though, is it's not just as easy as that always. In fact, we're not going to go into this in this class because we just don't have time, but there is something called factor analysis where you are looking at your model and you're saying, okay, I have age, I have height, and let's just say we add something else like maybe the amount of exercise that you get or maybe the amount of If you live in a mountainous area where the air is thinner, perhaps maybe those things. But the thing is, though, you can add those variables into your model, and you still have to figure out whether, for instance, those variables are helping or are they hindering your model. In other words, for instance, maybe the age of the person, that variable is actually a very important variable for this model. But when we add another variable, there is some overlap between that age variable and this other variable, which somehow mutes some quality of that variable, so that you don't get. It's like you're not getting the full impact of that variable. In other words, it's somehow being downplayed in a way that you don't get. You don't get. It's like you're somehow, your model is becoming weaker in some way. Even though you're adding more and more stuff, it's becoming weaker. I guess the best way of thinking about this is that if you have a car, and you fill up the car with half a tank of gas, and then you fill up the other half with water. Yes, you are adding more liquid to your gas tank, but it's not actually going to help your car. In fact, it's going to injure it. And so by adding more variables here, you may actually be injuring your model, which means that it's not as good. And so you need to watch your R² value, you need to watch your p-value to make sure that the model is still significant. But also, though, you can look at these values here, which are, how significant are these actual variables going into your model. So here we have 3 asterisks, which means over here that they are themselves significant. That means that age and height, according to this model, is a significant. They are significant variables. But there are other forms of analysis that you should still consider in factor analysis, where you're actually concentrating on the quality, if you will, of the model rather than the data. Like now you've built the model, or you've built several different models, and you're trying to figure out which models are better. Yes, sir. Yeah, that's right. So these are your test I guess your test statistics here, but you can look at your significance to see whether they are significant in the model. You might find, for instance, that let's say that I'm looking at my lung capacity, and I put another variable in here that's reads Sherlock Holmes. How much time do I spend reading Sherlock Holmes? I mean, that's maybe a variable that I'd throw in. Now, each of us here would consider that, yes, it's a variable, of course, but it doesn't seem like it's going to really impact the model in any way. And so you wouldn't expect to find a very significant value here. But this is just one way of looking at it. If you look at factor analysis, which is actually a whole class, if you will, in a graduate level scenario, if you look at that factor analysis, you'll see that there's actually ways of seeing whether, if it's significant, how significant is it, and if you remove it, is it going to make the model significant? There's another way of looking at, there's another type of regression you can look at, which is called stepwise regression, which is, again, kind of a model analysis. And what that's doing is it says, okay, if I have a whole bunch of variables, let's say I have age, I have height, I have the variable that talks about reading Sherlock Holmes and how much I read. Another one about how much exercise I get, how much, where I live, if I live in the countryside, or I live in some smoggy town, or wherever it is. If I live in the mountains, if I have variables like that, I can use this thing called stepwise regression, which will then make my model. It basically builds a model that looks exactly like this. But what it does is it alternates each of these different independent variables. It puts one in, it takes one out, and then it does the next one, takes that out, puts it in, and it basically makes all the possible combinations of models in which my variables are being added and then taken out. And the idea behind that is that it checks to see whether my p-value is still effective. In fact, if I find, for instance, that if I put age in there and I put height in there, and I also put in the quality of air where I live, or where the people live, the participants of this, if I find out, if I have that variable, you may find that that variable is much more important than whether or not that participant is reading Sherlock Holmes. And that's all done by stepwise regression. And again, stepwise regression, like factor analysis, those are both classes you could take that talk about how you can make a better model. But it's interesting, though, because here, up until this point, we're talking about the data, but now we have a model, And so now we're analyzing the model itself to see whether it's working, to see how well it's working. And I find that that's actually a very important, it's actually a very important consideration, that, that the quality of model, because if you're just working with models that are thrown together, you could potentially have a good p-value, and perhaps your adjusted r-squared value is also quite good. But if the variables themselves are just not very telling of what's going on with the dependent variable, then it's not a good model. It's like you're not going to learn anything out of it. It's like you still have a kind of a limitation, if you will. Anyhow, so there's that. And so that was really what we're spending a lot of our time talking about. Anyway, let's go back to the slides and pick up again. This is what we just did. We ran this summary down here. You have all these notes, by the way, in your slides. I do encourage you to spend some time and just play with these with this code here, just to get an idea about what it feels like to run this stuff, but also how to read the output that comes from the summary. I mean, actually spend some time looking at these things, because after a while, you can run hundreds of different models, and you'll just glance at this part down here, and you'll think, oh, okay, I'm looking at the adjusted, I'm looking at my p-value, okay, I'm happy, I'm going to move on to the next thing. But if you don't have the experience in doing that and looking at numbers that are good for your data, then you may have some limitations in what you can see and what you can study in your data. Here's your study, or your summary. We just went through some of these actual variables that are the coefficients that are actually somehow more important. If you're looking at, for instance, age, this age is the age in terms of in 1 year of age, we have this coefficient of 0.126. That's the increase that age, that's like the bearing that age has per year. And I think that for height, what we have here, height is it's the same kind of thing. We have 0.278 for every unit of height. That's the I guess if height is measured in feet, then I guess that for every foot we have 0.278. We have that effect on each foot. Anyway, that doesn't really matter too much right now, just as long as you remember that those coefficients are then poured into your line equation, which is right here. So for instance, that would be your age coefficient right here, and then your height coefficient would go right here. I guess they go right here. That'd be your coefficient there. This would be your coefficient for height. Age, so these are your coefficients, and then you'd have some other coefficient for your error. But your age and your height, these are the values that you could then put into your model to see what happens when I have age equals a certain thing and height equals something else. What effect does that have on my lung capacity? Well, all it's doing is it's running this equation to see where on the line your lung capacity value appears, and that is what your model is doing. Then we have these test statistics here. That was a question that we had earlier. What are these values at the end here? These are the test statistics to basically determine whether or not these variables are relevant. So for instance, the test statistic that we use to perform the hypothesis test for the slope for age equals 0. In other words, is age an important variable in our model? And so I will say, though, that just because you have this test statistic, though, don't stop there, though. You still have to go back and actually think to yourself, does it make sense for age to be there? Does it make sense for the height to be there? Is it a logical model? Because I guess what I'm getting at is causality well, you can't really tell. Just because you have a variable there doesn't mean that it's actually working with the model. It could just be a coincidence. It's not the causality thing is it's not causing anything to happen. It's just coincidental. So there's that to consider. Yeah, so we have all these other test statistics here, and then we're talking about the r-squared value. I tend to look at the adjusted, which is the value on the right-hand side. The multiple squared is maybe a more model-specific type of value, whereas the adjusted squared, or the adjusted r-squared, is maybe something you can use where you can compare across models. It's like a more universal value. Usually they're the same number, or very close, as they are here, but that doesn't mean that's always going to be. Then down here we have this F statistic, which is another, which is really how it's another test statistic, which is how R determines whether or not your p-value is a good, or the p-value is, determine what the p-value is. to see whether the model is any good. And this is what we would have done perhaps if this were maybe a pure statistics course where we had giant tables that we'd have to look up values in using our degrees of freedom and some other values. We have to look up on a table and find out what the p-value is. But luckily, because R is R, it has all that stuff built in, so it actually tells us what the p-value is. But it still gives us these values just in case. So anyway, this is where our null hypothesis comes from. We're saying that these are all, or the coefficients are all meaningless. They're all equal to 0. And that's our null hypothesis, or the HO. And that would be where that would be these equations. That's for this equation down here. Now these equations can be any length you like. You can have as many different variables in your model as you want. And we don't just stop at 3. You can have as many as you want, but remember though that you do have to test to make sure that these variables belong in your model, because you might find that they don't belong. You might find that they do not have significance in there, like these asterisks that we see here, for instance. They don't belong. They just don't. They have no bearing, for instance, on the dependent variable. They're pieces of data that were collected, but really have no relevance to the study. Finally, we have this p-value here, which is actually quite important to see how well, is there something random or non-random happening in our system. I would say that, for instance, if you look at the system and if you see a small p-value, if it's concluding that there is something non-random happening in the model, which means the p-value is very, very small, as it is here, then I would say that the model is probably good, provided that the variables, or the age and the height, are all significant. They're also significant themselves. But still, though, you can see that this is like your I guess, the goodness of your model in some ways. Yeah, so there's some more stuff here. Now, let me just talk about the one thing that we don't see here, but I wanted to give you I wanted to talk about this anyway, is the residual standard errors. Now, remember what these residuals are. The word residual, I think it's a misleading term. It is misleading because when you put these points on your, when you plot like the study time and the grades for some students, suppose you do some you have some research here where you find out how much time a student spent studying and what the grade was that the student got on the tests that they were studying for. These are all the points you get here, and so you're building a model to try and say that the more studying you spend, the better your grades get. But another thing you can look at is you're looking at, when you're building a model here, you have to look at, for instance, what's called the residuals. And the residuals are the actual measurements between the amount of, this is like your RSS value, but it's the measurement between where the points fell and where the expected line was in general. So for instance, here, I build my model and I put together my linear regression line, that's my model line. And I'm finding that, for instance, these points are found really not very close to that line. That suggests to me that there's like a lot of play between the line and any points. The longer the arrow here, the more play there is. And so this is like your measurements here. You want to have your measurements. You want to have your arrows that we see here as short as, or as short as possible. You don't want to have too much play between where the model suggests the points should land and where the points actually do land. And so we have these, we have to worry about the residuals. Now I have some plots in a moment here at the end of these slides that we're going to go back to this subject. But I wanted just to kind of go into some other analyses you can do that you can look at before we talk about the residuals. So here I'm going to look at the correlation of my variables. And if I go to my R squared, let's see if I can go here, right? I'm just going to dump this code in that I got from my slides. Oops, that doesn't look very nice. I put my library in here again. I probably don't need to do that. But the reason why I'm putting that in there is because when I run my what's called the pairs panels, this is something that we got out of our lab. Actually, you saw this in your lab perhaps. But we're looking at the kind of the correlation to see whether, before we can start looking at see how close the points are to where the model suggests they are, we should probably see whether there is any kind of correlation between those points at all. Now, I don't know why it's so hard to read on this screen here, but the values that we see from this pairs panel printout on in each box here we see on the right-hand side, those boxes contain the correlations of the a value of the intersected values here. So for instance, I'm looking at, if you look at the lung capacity, which is the box on the upper left, and you move over 2 spaces so that you're on the same column as where height is, you can see that the value is 0.91. Lung capacity and height seem to have a very big connection with each other. The correlation is very, very high. In fact, I can probably go over here. I can type in core, whoops, and I think that I can just go ahead and type in lung. I think this gets up my screen here. This is not, sorry. Let's put lung capacity, and I'll put, let's put here height. Okay, hopefully that'll make it easier. Let's spread this out a bit. Is that working? Okay, so if I just type in correlation here between these 2 variables, notice how I'm doing this? I'm doing this by saying, go to this data set, find this column, that's my lung cap, go to this data set, and then this money sign here means find, and then height. So really I have 2 different columns of data that I'm looking at here. But what this means though is this 0.91, that suggests to me, and in fact that's the same value that I see in my box, but that suggests to me that there is some correlation between lung capacity and height, which means that my model, which I created earlier, right up here, where I'm looking at height, and I have lung capacity in there. In fact, look over here. If I have lung capacity and I have height, that suggests to me that these 2 variables belong in the model. They do belong there somehow. I don't know how they do. I don't know what the effect is. I just know that the numbers seem to work out. Now let's look at the age and see what age is saying here. So if I go back up to here and see age, in fact, I can look at my plot and see what age is, but I'll just go ahead and type it in here just because I think it might be easier just to see it on the screen. Age, you can see, is actually quite a high value too, and that's 81. 82, I guess you can think of it. And I can see that also by looking at my pairs panels plot. And if I look at the age column, which is my second over, and I see where that intersects with, if I'm moving along on my x-axis, where do I intersect on my y with the other one here. So let's see, if I'm looking at lung capacity and age. So I guess what I have to do is I have to go up. So I'm at age, I move up, and that intersects where lung capacity is. That value is 0.82, and that's the value that we see down here. So the correlations are high. Now you can also add other things into your model, but I don't see any numbers which are as high as that, which suggests to me that because, going back to the model here, because I have this adjusted R² value of 84, this one right here, because I have that value of 84 and I'm looking at my pairs panels plot, it's going to be kind of hard to say, my correlations plot, because I don't see any other variables which are as high as that, it suggests to me that perhaps I don't have the variable. It's just a hunch. It's just a hunch that comes to mind, but it's suggesting to me that maybe in my data set, in other words, maybe in this data, I don't have the variable that would give me the other 15% of my model. There's something missing. There's something that could be there that would actually provide much more detail, but I still don't have that yet. Anyhow, so you have that. Here's another one you can look at where we're actually looking at a pairs panel where we're looking at the actual, we're using our models, our regression here as our model. So again, the numbers should be the same if you look at the, this is kind of funny here, there we are. The numbers are the same, the correlation numbers should be the same, but now I'm looking at the left-hand side, and I can see many plots where I can see kind of like the line, the regression line, where that is, and where my points are falling. And so that's kind of telling me, getting back to the residuals, that plot that I'm seeing there, like for instance, if I look at the age, if I look at the, if I start at age and I move to the left, and I'm looking at the column where lung capacity is, that plot shows me that all the points appear to be following my regression line, or my linear model line. And so that's that point that we see there, that's kind of like the center of my data, on the red point, that's the center of my data, but the line though is really where I want my points to fall. And so I can look at that, and I can just say at a glance, the correlation is good, and the model seems to be a good fit. It seems to be a good fit. But this isn't the factor analysis that I was talking about earlier, where I can actually see whether those factors are actually any good. And also, it's hard to see whether there's anything. It's also hard to see whether, for instance, my residuals are small enough so that even though I have a nice line that goes through, maybe, for instance, my points are not as closely stacked to my line as they could. In other words, if I'm putting in my own age and if I'm using my model to predict something, when I'm putting my own age and height data into the model, maybe, for instance, I'm landing on the line, but that's actually very, very far away from where the points would naturally go. So in other words, I have this inaccuracy. So there is that to think about. But I mean, there's a whole science behind these models here. So this is your correlation that I just got done talking about, the age and height. You can see 84. I'm looking at the age, and you can see the height. You can kind of get an idea about where they intersect, and that's where your correlation value is. You can still type in, for instance, core, as we just did, to actually get to that number. So if you actually if you're writing code, for instance, where you need to pick something up, you need to pick up some correlation value. If you actually know what the variables are that you're looking at, then you can actually just type in core and get right to that correlation value. The method is always Pearson. There's other correlations, but I think that in general, using a Pearson method is good enough for core. Yeah. This is again the code that I just typed in, so it's all there. You don't have to worry about finding it. But really, though, this is seeing. Remember, this correlation is seeing whether or not age in some way should belong in our model. And if you look at these other correlation values here, that can give you some ideas about what else you should add. Like, for instance, you might add. It looks like height and smoking seem to have some kind of correlation. Looks like age and smoking seem to have some kind of correlation. For instance, age and smoking is 0.21, but that doesn't tell me anything about really. I mean, I would argue that just age and smoking doesn't necessarily tell me anything about the lung capacity. What that does tell me is that age and smoking usually, I mean, you don't expect children to be smoking. You know, you just don't. I mean, I hope you don't. I hope you don't. But so the data is going to be skewed, and it's going to be naturally biased, and it's going to have natural problems that are inherent in the data collection, which are going to influence that correlation. And so you always have to think about that in terms of the in terms of what you're studying. Also, for instance, like age and height, that's a correlation, but that's not necessarily a correlation that has anything to do, I would say, per se, with the lung capacity. It tends to be that as you grow older, you get taller. It just happens that way. I mean, you never really see, giant children. They usually become giants when they're in college, and then they're towering over me. But what I'm saying is, you tend to find that age and height are correlated, but that's not because of this data. That's just because of the natural growing. This is something that we spent some time talking about in my other class in bioinformatics, where we look at certain types of data sets, and then we try and figure out how we can model that data based upon the natural rhythms of biology, if you will, which control that data. So, for instance, how can you model how height and age are connected? Well, it just happens to be that as someone grows older, they get taller. So therefore, that is the model. The model has to center around that in some way. Whereas this is different because age and height are being shown that they are correlated, but there's no suggestion about why that correlation exists. We have to spend some time thinking about that. And in this case, I would suggest that it's kind of easy to figure that out. But in some data sets, though, it's not easy. But once you find out what it is, then you might think to yourself, oh, of course. Especially, for instance, if you're looking at like financial information or financial data, you might think, why is it that people who bought an iPod 2 years ago are now buying iPhones? Like, why is that happening? The data would suggest that is happening, but you have to actually go back to the people and maybe do a follow-up survey or ask more questions before you can really explain what's going on. Anyway, so what I'm saying is that the model doesn't tell you everything. You still have to go back and do more research to find out what's going on. One thing I wanted to talk about, though, was actually, this isn't the most recent slides I was working with. Sorry, let's get back here. Okay. So yeah, these are my updated slides. I wanted to talk about, for instance, these residuals. Let's get back to those. And so now what I'm doing is I'm going to create a bigger model where I'm going to be talking about the height, smoke, gender, and the Caesarean factor. So let me just go ahead and copy all this stuff into this is like my whole model. This is all the data that I have. I'm just throwing everything that I have at this model. And so if I go back to R, I'm going to find, here we go. I'll just dump everything in. Let me minimize this so I can get everything on one line. I'm making mod 2, which is my model. I'm going to look at my summary. I can see that it's still significant. I can see that by looking at my data or my variables in my model, I can see that there are some things that are significant. I guess it makes sense that they're significant. But note, for instance, that the significance is not the same. So, for instance, we have smoky, I guess smokes. This is the gender. And this is the Caesarean. You can see that, for instance, the Caesarean is a variable, yes, but it is not extraordinarily significant. I mean, it's just barely there. It just has this one star, and that one star is this guy over here. So it's still, you can still publish this result and stick it in there and say this is significant, but it's not all that significant compared to the other guys who have 3 stars. But what I would like to say, though, is that remember that when we made this model before, where we threw in just age and height, remember we had an 85 or 84% or 84 adjusted R squared? Well, look at this. So I've just thrown in whether they smoke, what their genders, and whether they were born Caesarean, 3 more variables, and it's made this thing go up just basically 0.5%. It hasn't actually affected the adjusted R squared that much. And so this is really what something like factor analysis would tell you, and that is that some of these factors, while they are data and they could be useful for some types of projects, in this particular case, they're not telling much. They don't give you much extra information. And also you can see though that, for instance, I mean, it doesn't really make much sense. I've added 3 more things and it hasn't really changed it hasn't changed this much. And so that says to me that the data that I'm actually looking for may not be in my data set. In other words, click on my data set here. I don't have the data. I need to get back and collect more information from each of these participants. This becomes different, by the way. Let me just say something on this, and that is that supposing that I do create a data set like this from participants, and they've all then I've thanked them very much for their time. I've given them their whatever it is, their free pen or their $2 or whatever they got for doing this survey. I say $2 because sometimes when you do some surveys, you actually do get $1. It's funny, but still, you do get paid in some way. But the thing is, though, that now that these people have gone away, it's difficult to actually ask them to come back and provide more data. So, for instance, supposing I have lung capacity, age, height, smoking, gender, and Caesarean, but now I need to find out whether they live in the forest or whether they live in the mountains or whether they live in an area where there's lots of pollen, or is there something else that where they live that could explain, for instance, in other words, is there something else that could give me the extra 15% that I need to boost my model? It's difficult to have these people come back. And so what I'm saying is that when you're doing an experiment like this, when you're working with analysis like this, it is better when you're working with people to have as much information coming from them as you can possibly get. And that's a big ask. That's very, very difficult to ask them to do. But as much data as you possibly can so that it is all together, and you can go back and just like, okay, just change this and change that and add this and move your model pieces around and run your stepwise regression to kind of determine which of the model pieces that you need. Because otherwise, you may have to wait 6 months to look at these people and get the information. And in some cases, in many cases, these people are long gone and they'll never come back to your survey. And when you're asking people to do a survey, they're actually giving you quite a piece of their life, and some people don't like giving out that information. Okay, so we have our summary. One thing I wanted to show you though is there's this command here called plot mod 2, which is really this piece of the model here that we just created. And when I run this is actually quite interesting. Hopefully I can make this a bit bigger so that you can see what's going on. But you have 4 prepared models that R will give you. The first one is the residuals versus leverage. We don't really have to worry about that too much, but this is really what's called the Cook's distance. That's a highly statistical value where you're seeing whether where these values, like what the general trends, where these points tend to congregate. Like what's the I guess it's like you're studying something about the how far they are from the residuals. I'm not going to talk about that, but what I wanted to talk about though was, oops, I'll get my next plot here. There we go. I wanted to talk about this, the residuals versus fitting. Now this is actually, this goes back to a previous conversation that we began, where we were talking about before the correlation, right here, the residual standard error. Like how far away are these points from the model? I created this dotted line here, that's my model. I want to know in general, how collected around that model are my points. In other words, if I run some kind of analysis, I'm basically looking at points that are on this line. How far away are those points from actual points that would be there under similar circumstances? In other words, how long are these arrows? And so I have these plots that I'm putting together, and that one of those plots is called the residuals versus fitted. And so this is going to be one of those plots that's going to tell you, in general, how closely aligned your model is with the points you get. So this is actually kind of tricky to think of, but just bear with me for a moment here, and we'll go through it. But remember that each point here is not the data that we're looking at before. It's not the data. Instead, each point here is the distance, if you will. It's the distance of each of these arrows here. It's the distance from the model to that point. The distance, that's all it is. And so you have, in fact, you'll see that there are some similarities, and you should see some similarities between this plot and your own plot when you actually plot the data. But these points are the distance. So that means that this red line, hopefully you can see the red line, it's kind of hard to see, but it is there. There's a red line that cuts right through the middle at 0. And so this means that any point that you see here, any residual point that lands on this red line is saying that that's a point that actually landed on the model. That means on the line. There was 0 distance between that point and the points that we and the model itself. There's just 0 difference between where the model landed, where the model was drawn, and the actual points in the data set where they landed. So that's, remember, the distance you see between the point and the line is kind of like the goodness of fit. That's what this is all about here. And so this line here we have here is what we call the expected, in this case here, maybe say expected, but that's the model that we've created. And so we have 2 different points here. We have the estimated, which is where the expected should be, and then we have the actual data point itself. And the data point is the data that we see in our actual spreadsheet that we were looking at before. So we're trying to figure out like how far is a point land in real life, a real life point landing from where we thought it was going to land. And so if it's 0, that means the point and the model landed in the same place. That means that they're exactly the same value. However, you can see some points here where I'm looking at like this point 270 in the plot. You can see on the left-hand side, upper left-hand middle. That's a point which is actually quite far away from where the model is. That could be an outlier. We use these plots to see whether they're outliers. Outliers, remember, those are those points that land far, far away from where we expect them to land. That's an outlier. And so here we're saying that this is a point that landed very far away from where the line was that the model created. And so that means that this is a point 270, which could be an outlier, or maybe it's the truth, who knows, maybe our model is no good. But in general, what you're looking at is when you're looking at these residual versus fitted, you're looking to see that your points do kind of cluster around that line. In fact, you're making a band of those points, and your line at 0, x or y equals 0, really has those points on either side. And remember, those points are really just, that we see here, those are distances between how far above or below those lines are, or rather those points are from our model. To make that a little bit more clearly understood, there's a picture here. The residual value. So this is our we're actually figuring out what the residual values are. We're making some plots for residuals. And the residual value is found by taking the expected value, which is where the model is, which is our blue line that we see here, And I just put as 0 to make things easy, but it's a value. And then we have this yd value, which is going to be our y that's on the data. It's a data point. In some books, you'll see that it's like that's actually y sub I, and then the expected is y hat sub I. But because I couldn't put hats in here, I just used this new way of calling the points, but actually they are the same. And so then I get this value here called residual, which is subtracting 0, which is the expected, from where the point actually landed. And so that's where this residual value comes from. Now this residual value, when I do the same calculation for all my points, I plot those residual values, I get something like this. And I'm trying to see how far away from the 0 line those points have landed. And so if I do this calculation here, and I find that after I've created my model here, and I'm looking to see where the points actually did land according to my model, if I found that those points were nowhere near my model, then something bad happened to my model. That means that the model wasn't created properly. There's much to say about this, and I don't mean to kind of get carried away. I wanted to kind of move on to some other things here, but there are many, many things, and I do encourage you, if you're interested, to spend some time looking up these residual versus fitted plots, which you'll see here. There's much written about them, and there are people who just work with these. That's all they do. You have a model, you build, and then you hand this residual versus fitted plot to one of your people in your lab, and this is all they work with, just this. And then they determine whether or not your model is any good from this information alone. So it does take some time. Excuse me. So here's really what this is about. Any point that we find from real life data that falls on our model is going to have a residual value of 0, because that's the residual values are. It's the distance between the model and the point. And so if you have a residual value of 0, that means the point actually fell on the regression line, which is a good thing, because that says that our model is accurate. It's actually showing some level of appropriateness of our model. So what these things do is, I just put this down as suggestions of appropriateness. I know that's probably not the best way of describing this, but really what these plots tell us is how good is that model in a very basic sense. How good is anything we learn from this model going to be? And so we have 3 main suggestions here, and one suggestion is that because these residuals are these distances, residuals, distances, same thing, but because these residuals are scattered around this y equals 0 line, there's like a band of these things here, which kind of like they're generally scattered, they're situated around this line. It means that in general the points are falling close to the model. That means that if I were to actually use this model and do some predictive work, I could argue that enough points have fallen from my data set on this model to suggest that any points that I use as predictions points, or any points that I predict, are actually good data, because those points could also be found in this swarm of points. If you found, for instance, that your model and the points were like nowhere near each other, then it means that anything you predict is going to be on that red line. That's your expected, and where the actual points are landing, it's going to be somewhere else. It's not a good fit. So this suggests that the assumption that the relationship is linear is reasonable. In other words, this is a good. Our points are actually able to be predicted in some general way by the model. The second suggestion that we have here is that because these points are kind of like creating what's called the horizontal band, where you have like this stretch of clouds, where they're really kind of following the line, the expected line, in a very kind of uniform sense. I mean, you could argue that it isn't, but you could say that in general it is a uniform collection of points that kind of follows that line through the middle. It's saying that the variances of the error terms are equal. And that means that the variance is actually one of the requirements of your models here. But you're saying that the variances of the error terms are about equal, which is a good thing. That means your model actually is important. Now, if you were to plot this again, and you found these points were like nowhere near where the line was, it means that the variances, or the growth of some of these values, is not the same. So therefore, your predictions may follow a different variance, which means that you're actually predicting different things. which is not being represented by the data itself. And so you want to have but basically what I'm saying is you want to have your plots looking like this, where you have everything kind of like gathered around the line. The third main suggestion is that you see that there are some residuals which are standing out. Notably, you see the 270, 641, and 136. These are actually categorized by R as potential outliers. There's only a few of them, though, not too many, only 3 of them. There are other points you could say are outliers, but these are the ones that R has flagged, saying, these are actually really out there. Maybe you should consider that these are outliers. And so what this is doing is it's saying, how many outliers are actually in my data? Now, you always expect to find a few outliers in your data set. And this could represent maybe bad data collection. Maybe it's the truth, who knows? Maybe they're just unusual findings. But in general, though, to make a good model, you want to be able to have the points kind of gathering, the points you collect kind of gathering in the same place, so that you have some assurance that anything you predict on that, anything you predict in your model is going to be a point which you could potentially find in that cloud. If you find that all of your points are outliers, then that means you have really no idea where the points are going to land when you predict them, and that means that it may not be. I mean, of course, you know where they're going to land, but is that representative of what the real world is doing? So what I'm trying to say, though, is that because you have these outliers, 270, 641, and 136, I think those are the going down the data. That's the row that they're found on. This would suggest to you, for instance, maybe those outliers need some explanation. Typically, when you're working with if you're publishing this work and you have a whole lot of outliers, I mean, like a whole bunch of them, it would do you well to investigate those outliers and talk about how those are outliers. And then you may find that they are outliers, but maybe that's actually another study waiting to happen. Maybe that's nested data in your set. So anyway, you have, I think, all the the basics of doing multiple linear regression now. There are many, many, many more things that I did not mention, just because we don't have time to go through all of these, which is sad. I mean, this is a regression is actually, you could actually break it down to maybe a full year-long course, regression 1 and regression 2, and in that course, you'd spend all the time studying all these different plots that you'd see in your studies of the model's appropriateness. But there are many, many different things to do, and if you are interested in pursuing more regression analysis, I recommend to find a good book on linear regression and read it. There's a lot of stuff there. The book that I had when I did linear regression, I think it was like it weighed a ton. It weighed more than my laptop, and it was like 400 pages of just regression stuff. And so there is a lot of learning out there to be done. So if you are interested, I do invite you to spend some time looking it up. There's YouTube videos and some other things that might be helpful to you. Are there any questions before I move on to the next thing? Yes, sir.
So if we go back to the summary of the previous model, the p-value at the bottom, is that present the p-value of the model?
Of this?
Of the model as a whole, and how significant it is?
Yeah, so the question is, if we go back to the original model where we had lung capacity being regressed by age and height, then we look at this p-value down here, which is less than 2.2 times 10 to the negative 16, which is a tiny value. This is a value saying that this model, as it stands, is significant. That's like there is something here, right here. There is something non-random happening in this model, but also that this model is a meaningful model, arguably. Arguably. I say arguably, I'm saying that this model would be the one you'd use, but the thing is you still need to go back and check, because age and heights, just because they're significant doesn't mean that they're actually really having anything to do with lung capacity, which is a real nightmare, actually, when you're working with data, because you might find that you find some data sets, the way that they're collected with the biases involved, you might find that there appears to be some kind of connection, but that doesn't necessarily mean causality. So for instance, if you were to poll people and find out when they really enjoy flying, I would imagine that most people on planes when would they most likely enjoy? When would they most likely fly? Most people, I would say, would catch like the early flights, the morning flights. Because why? Because they're business people. They're flying somewhere for business, or they go on vacation. They want to get a start, or maybe they have to get out of the house before the cleaner gets there. Who knows? But people tend to like to fly in the morning just because that's the human condition. Now, if you collected data on when people fly airplanes, you'll find that that most of the data would point to people flying in the morning. Just most of it would. And because that is another thing is that because that's well known that people like to fly in the morning, most of the airline companies and airports plan their flights so they leave in the morning. So then you have to fly in the morning. So if you're doing a study to say when do people most likely select a flight, you'll find that most people select their flights in the morning because that is the human condition, which is somehow informed when the airports actually have planes taking off. So what I'm saying is that's a bias right there. It doesn't mean that, for instance, that when you look at the model, it doesn't mean that those two values, the morning time and the flights, I don't know, the morning or I guess the time in the morning when flights take off and people's tendencies to select them. It doesn't mean that those are that one thing is controlling the other. It means it's a correlation, but the actual reason for that correlation is that the airlines only schedule flights in the morning, and so it's like you don't have any. There's no other way to fly, and so that's what they call a bias, where you are your correlation is up there. It's very high. It looks like there's like one thing is explaining the other. But actually, they're two independent variables, really, that have really nothing to do with each other, but they are bound by this bias of the human condition. Like another one might be, for instance, when do most people enjoy having lunch? Well, it's kind of traditional to have lunch at 12. And so most people say, oh, I have my lunch at 12. Some outliers may exist where they have lunch at like 10:30, and other outliers where they have lunch at 3, but in general, most people have lunch at 12 because that's when they start getting hungry. But because people select to have lunch at 12, and because restaurants start opening up at 12, that is a correlation, but it's a very biased correlation because that's just the way that the nature of the system works. This happens. That's a very good question. That's a very, very good question. This happens in biology all the time when you're working with different models. You find that some models they seem to have some variable in the model seems to have some very strong connection with something else. But actually, when you spend more time analyzing it, you find out that it's not it's explained by some bias that exists. One thing I wanted to do with the time that we have left, how much time do we have? We have about 10 minutes. I'm going to see how much I can get through. But I wanted, though, for your own peace of mind, I wanted to go back through this lab 4, which was actually a very important lab, and I think that actually. Where we are today with the COVID-19 pandemic, I think that perhaps we could all do well to kind of go through the study of vaccines, not for COVID, but for mumps and measles. And so that's really part of the inspiration behind this lab that we had on the 28th of September. But now that the labs are all in, I wanted to spend some time to kind of go through what it is that the big lessons that we're learning in this thing. And so I did the lab myself. Of course I did. But I wanted to take you through kind of like my thinking behind some of these things because I think that maybe it's interesting. So we're going to talk about vaccines for a second, the vaccine lab. And the big question that's with any vaccine when it comes out is that vaccine working? So for instance, there were, for this lab, we're talking about measles, mumps, hepatitis A and B, and some other things. And these were serious problems in the 1960s and before. I mean, people were dying. I mean, it was like it wasn't, I would say it probably wasn't as bad perhaps as the fear that we have today of COVID. It's hard to say that though, but I would imagine. But it was up there. People were very afraid. People did a lot of hand washing. They did a lot of, they were grooming themselves, making sure that they were taking care of themselves. They did as much as they could to avoid getting measles and mumps and hepatitis A and B, because these were illnesses that seemed to spread around very, very rapidly. And so parents were very afraid for their children who would spend time with other children who may have had these, who may also have these. Anyway, so what I'm trying to say, though, is that vaccines were very much required in these days to remove measles, mumps, and hepatitis be from the population. So once those vaccines were out, we had to ask ourselves, do they work? Are they doing anything? And when do we use them? So in this graph here, this is just a this is a graph that was actually created more recently than 1950s, obviously. But you can see that these, I'll just give you an overview here. These are points when vaccines were issued. On the x-axis, we see the year. On the y-axis, we see the mumps incidence. These are cases of cases per 100,000 people in the population. So each data point is really how many people got or how many people got a case of the mumps. One more thing I'll tell you about is we do not see here. We don't see the actual data points, but rather we see the smooth line, and we've worked with smooth lines before. And so this is the line that's describing the trend, but we don't actually see the points themselves. And so we already have some kind of limitation. But this is enough. This is enough to get an idea about how the points are moving. And you can see that where each point is, where each peak is, I'm looking at, for instance, the licensure of trivalent MMR. That was a vaccine that was given out. And you can see that the cases were climbing in 1970. And then once a vaccine came out, they began to decline. And then, of course, there's a recommendation for routine use of single-dose MMR vaccine for children who are greater than 12 months of age, in other words, children who are a year old. You can see that, again, that seemed to have some effect on the cases, because the cases at that specific point, you can see a kind of a curve that happened where the cases kind of dropped off. And then again, you can see that everywhere that these vaccines were actually given, the cases, it changed the cases. And so what we're looking at, though, is like, do we have any information about these vaccines working? Well, we're looking at the number of people who got sick when we're comparing the people who got sick with the people who received the vaccine to see whether there was any kind of change in the numbers of cases that were going up. And so we ask ourselves, do vaccines work? And the best way to find out whether they work is to do exactly that, by looking at the cases to see whether, when somebody gets a vaccine, does that make the cases drop? Do the number of cases actually become fewer once a vaccine has been given? Now, this is especially relevant for us today in our time, because we're looking at the potential vaccine that's coming out with COVID-19. I found in the news that Pfizer has released a vaccine which is 90% effective, and that means that 90%, or 9 people in 10, will show signs of immunity to COVID-19 when they have this vaccine in their system. There's always the one person, though, who won't have immunity, and that's probably because of other kinds of biological factors. Maybe they're born with some strange blood type, or who knows, maybe not blood type, but maybe there's something else going on in their system which prevents the vaccine from working. But 90% is actually an excellent number, because typically you'd expect a vaccine to be like at 60% or something even less than that. You try and get as high as you can, but you can't always get everything. But what we're looking at now in this table is we have smallpox, diphtheria, pertussis, polio, measles, mumps, rubella. I'm actually looking at the measles here. But you can see that in the 20th century annual morbidity, what that's saying is like the traditional infection rate of these things is actually quite high. Looking at this, you can see that, for instance, pertussis is at 200,000, measles is at 530,000. These are some of the more pressing issues for which vaccines are necessary. And you can see that, for instance, that once the vaccines have been given out, in 2010, for instance, long after vaccines have been established and given out seemingly at the first year of birth, after birth, the cases have gone down. And so we have, for instance, 21,291 for pertussis, and then we have mumps. We have 2,528 cases reported in 2010. Now, those cases could be because those children, or whoever they were, those people were not given vaccines when they were little. There are a group of people out there who still believe that vaccines are bad, and we've discussed that, and actually in this lab itself, where we had the paper that came out saying that vaccines cause certain types of autism, which is not true. That's been completely debunked. There's no connection at all. But there are some parents out there who still believe, and that belief prevents them from having vaccines, and so that could explain some of these reported cases that we're seeing here. But in general, we're expecting to find the 20th century annual morbidity rates to be, or cases, to be generally higher than the ones that are more recent, where the children or the young adults have had the vaccine dose. So this is really what I wanted you to see, though. When you run this code, and I don't think I have to run this code right now, but I have the plots here, and so I invite you to run it just in the interest of time. This is exactly the graph that I wanted you to see, and that is that, remember, each of these points here is the contagious diseases in the U.S. This is the mumps and measles. And this line, I think that actually we're looking at measles in this case, but this line that we see cuts through 1964. Or 1965, that's your x-intercept line, it's in red. And what that line represents is the date when vaccines were introduced. When did children start getting vaccines? That's the line, that's like the divider line where you see the chaos from the points before, where the cases were all over the place, to controlling the cases. You still have cases after 1965, but you have many, many fewer cases, and you have really flattened the curve. So that suggests, just by looking at this plot here, that vaccines are making a difference. I mean, it could be other stuff, but because the data that we have here is primarily about cases before and after vaccines were given, we can safely assume that vaccines have actually prevented many cases from happening. And so that line here is actually, this is extremely significant as a finding, because it's saying that the vaccines are making a difference, they are working. I'm looking forward to, for instance, for this COVID vaccine that's coming out, I'm looking forward to seeing similar types of plots where, for instance, we'll have 2021. I think that they're saying that in the spring of 2021, most of the population in the United States and the rest of the world will have a dose of this vaccine. And so we should be seeing in our own country and the world around us, we should be seeing the cases beginning to subside with a big red bar that goes through 2021. Or maybe in some cases in 2020. But we should see that the case is coming under control, and that's really what this is all about here. So then we could do some more information here. We can look into this. Here's some code that you can do. This was the equation that I offered in the lab here, where I was asking you to put together the count and population and the weeks and the reporting. This is the rate. This is like how many. This is like your variable that you can use to kind of keep track of the count in the population and the number of cases according for a year. And the equation is basically just put together with everything there, with all these variables in there. But the thing is, though, that you can use this rate now as your data that you can see whether you're actually able to keep you're able to keep an eye now on the count in the population and by year of the cases. Anyway, that's what that's there for. But then we trimmed out the two states. We actually removed Alaska and Hawaii. That was because I think back in those days, those states were too young to really be considered as a part of the country back in the early days. So that's why they were removed, just because they were states that were added last to the country. And so this is the code that you'd have for that. But when you actually put that together and you plotted it, then you have this. This is the same. This plot over here is the same as this up here, I think. But this is the plot that you have. And again, you can see that the points were all over the place. And then once that 1963 or 1964 to 1965, once that time had come around, when vaccines had become more readily available, then you can see that the points actually did become quite flat. They became much more flattened, which suggests that the cases were reduced or prevented by this vaccine. We focus on California in this lab. That was, and I call this Califocus, and that is because California was just selected as one of those states that would be a kind of a representative of the rest of the country. The idea being is that you have fewer data points to worry about, fewer things to plot, but still it's a good representation of the rest of the data. And so, looking at just the California data, you can see that the cases are all over the place between 1940, 1950, 1960, but then after 1963, in this case, you can see that they begin to come down. We begin to get a control over measles. So one thing that we didn't actually talk about, I think we're almost out of time now, and maybe we'll come back and talk about this on Tuesday, was transformations. I had to use some transformations to help out with some of the visual work here. But just suffice it to say that when I run a transformation, what I'm doing is I'm just taking the data and I'm changing it mathematically so that I'm able to kind of get more things on my canvas without everything kind of like running off into obscurity. Here, for instance, I have some transformations. I have the regular data, which is just well, which is my orangey color here, my orange what do you call it, my line here. But when I can't see the other lines on my plot here because by contrast they're getting much more squashed down. So if I transform my data, then I get an idea about how one thing is growing from another thing. Anyway, maybe I'll stop it here. We're out of time. But when we come back, I'll wrap this up, and then we will move on with the rest of our week next Tuesday. I don't think that we have to worry about a lab meeting to this, or actually do we? Yes, I'm sorry, we do. We have a speaker. That's right. There's no assignment, but that doesn't mean I don't want you to be there. I want you to be there. I'm not going to give another lab because I'm getting tired of grading labs. I'm still trying to get through the other labs that you've given me. So I'm thinking that we won't have another lab, but please afford me the time of coming to listen to Dr. Anyi Wu from the economics department. He is a wonderful, wonderful speaker, and when you listen to him talk, you're just like, wow.